Process synchronization. Before learning what process synchronization is, we need to know of a condition called race condition. Race condition means whenever more than one process is accessing a common resource or a shared resource at the same time, then there occurs inconsistency in data, which in turn leads to unexpected behavior in the program, in the way the program works. So, the main reason why we need process synchronization is because when we have multiple processes sharing a resource, then we need to avoid both of them accessing the resource at the same time. If not, that leads to inconsistency in data, which itself in turn leads to unexpected behavior. So the whole reason why we have process synchronization is to avoid this race condition, that is unexpected behavior in the program. So there are multiple ways to perform this process synchronization. That can be the Peterson solution, or hardware solutions of synchronization, which is called handling critical section, solution in which we have test and set, swap, lock, and then we also have semaphores and then monitors. So these are some different ways to implement process synchronization, and before learning any of these, we must know how we are handling a shared resource. So whenever we have a shared resource, then the part of the program in which we are accessing the shared resource is called a critical section. Critical section means the part of the program where we are accessing the shared resource. Now, the program, any process in which we are accessing a shared resource, its structure is as follows. We have a entry section, we have a critical section, we have an exit section. So whenever we are accessing the critical section, whenever we are about to access the critical section, inside the entry section, what we need to do is we need to check whether the critical section or whether the shared resource is available to be accessed or not. And whenever we are leaving the critical section, then inside the entry section, we need to check whether we need to perform some operations to make the shared resource available for the coming processes. So these are the two actions that we need to perform in the entry and exit section before and after entering the critical section. And now this is the basic structure. And now coming to Peterson solution. Peterson solution is the hardware, is a software solution for handling of a shared resource. That is, this Peterson solution is only accessible, is only feasible, or can only be used when we have two processes. First one is the software solution. We must have two processes only. And this Peterson solution is used whenever we are only having one instance of the resource. So whenever we are having more than one instance of the resource, we can't use the Peterson solution, that is the software solutions for process synchronization, handling of critical sections, or the hardware solutions for the three hardware solutions that are mentioned previously. We can't use any of these four solutions. So the way this Peterson the three conditions for using the Peterson solution are this, and the structure of a Peterson solution is for a process I. For process I, the structure is as follows. Initially, we are having two variables, flag of 2. This is a two-dimensional array here, which is initialized to false and false. And we also have another shared variable called turn, which has a value of 0 or 1. Here the turn value 0 refers to the state when the process that has the access to the shared resource is the first process, and the turn value 1 refers to when the process the second process is what has the access to the shared resource, and the flag condition, flag of 0 and 1 tell whether the process 0 or process 1 are interested to enter into the critical section or not. So now the algorithm is as follows. Initially both of them are false, and the turn will be 0. Now for process I, if I equals to 0, then we also have another variable called j inside this process, and then j will be 1. If I equals to 1, then j will be 0. Contradictive. Now inside this process we are going to have flag of I equals true, set to true, and turn equals j. And after this we are going to have an infinite while loop where we are taking flag of j and turn equals j, which is going into an infinite loop. And now after this we are handling the critical section, and then flag of I is going to be false. So this is the algorithm for handling critical section via Peterson solution. Here what's happening is, whenever we are calling the process 0, the first process, then it's setting its flag to true, that is it's interested in accessing the shared resource, and it's giving a chance to the other process, which is, if it's process 1, then it's giving a chance to process 2, and if it's process 2, then it's giving chance to process 1, and it's checking if it's interested or not. Inside this while loop, it's checking if the other process is interested or not, and if it is interested, then we are already giving the turn to it. So it's interested and we are giving the turn to it, meaning that that process is going to access the shared resource and complete its execution. And once it's done, this flag is going to be false inside the code, like whatever statement that will have the flag of I equals to false in that particular program. And once that's done, once this becomes false, then we are proceeding with accessing the critical section in our program. So this is it for the Peterson solution. And then the next one will be hardware solutions. Inside the hardware solutions, we have 3 test and set, swap, and lock and unlock. So now these are the 3 solutions available. First, let's check test and set. The algorithm for test and set is as follows. And before talking about the algorithm, here we will have a variable called lock, which is initially set to false. And whenever a process is the process accessing trying to access the critical section, then what happening is as follow: while 1, while test and set of this lock, test and set of lock, infinite loop, and then critical section, lock equals to false. So this is the structure of our program, and here the definition for the test and set will be test and set of lock, and inside this test and set, initially we are checking bool of rt, which is the return value. Here this is a temporary variable which holds the value of lock whenever it enters the process initially, and lock will always be set to true and we are going to return RT, which is the value of lock when it enters the process. So now, how this is going to work is, now let us consider a process P0. A process P0 is entering into the is trying to access the critical section initially. So now, initially the value of the lock is false, and when it's accessing the critical section, then what's happening is we are calling this function inside the loop. We are calling the function test and set, and inside this test and set function, the value of lock will be false. So when the test and set function is called here, test and set of lock, test and set of false, the return value here, the RT value will be recorded as RT equals to false, and the lock value will be set to true. And once the lock value is set to true, this false is returned. The initial value of lock when it entered the function is returned. Now, what's returned here is false. So initially at this time we are having false as the return value, meaning this while loop won't be executed and the access to the critical section is given to the process P0. And now once P0 is inside the critical section, when P0 is in the critical section, we are having another process P1 which is entering the critical section and which is trying to access the critical section, and now we are calling for P1 again, we are calling the while test, this function test and set inside the while loop, and here the value of the lock has been changed here. The value of lock has been changed to true by P0, and so now because it is true, when P1 is calling the test and set function, the value of the lock will be true, and the value of the lock will be true, and when it is entering the test and set function, when it is entering the test and set function, here RT will be set to true, and again we are trying to change we are trying to set the lock value as true, which is happening every time. But if you just leave it as it is, because it's happening every time, now the true value will be returned. Here initially lock value is true, so now that's recorded into the RT value, which is the value that we are going to return, our RT variable. Now RT is returned, and here what we are getting from this test and set function is true. So the way it works is, when the lock is false, that means no process is having access to the critical section. That is, no process is accessing the shared resource, shared resource. So it sets the lock to true, meaning that it gives access to it, meaning that a process is accessing the shared resource, and it returns false to this, which meaning this loop will be terminated and the process that is trying to access the shared resource is started execution. And whenever the process P1 or again a process P2 is also accessing, then the lock value will be true here, meaning we are going to receive true until the process P0 is completed its execution and the lock value will be changed. And once P0 is completed its execution and the lock value will be set to false, then this function, whenever P1 or P2 is calling the test and set function, here the value that is passed will be false, and here the RT value will be false, lock will be set to true as usual, and the value that is returned is false, meaning the loop, the infinite loop, the continuous loop that we are having until then, that is stopping P1 or P2 from accessing the shared resource, is going to stop because they are receiving the value false. So then it gives access to the critical section. So that's how this test and set solution works. That is, we are having a lock variable which will be set to true whenever a process is entering the critical section, and whenever other processes are trying to enter into the critical section. Because this lock is false, we are just gonna be staying in the loop until the previous process is done executed. And then we have the swap method. Here, this swap method is the same as is somewhat similar to the tested set, and inside we are having two variables again, lock which is set to false and then key which is set to false, and here inside we are going to have a function called swap of lock comma key, and inside this what we are doing is we are swapping temp a equals to lock equals to lock equals to key equals to a, and inside the program while one we are calling a while loop, while key swap of lock comma key. Initially key value will be individual for each process and it is initially set to true. So here what's happening is whenever a process is trying to enter into the critical section, here we have a variable that is individual to each program called key, and by that is set to true, and the condition here for entering the critical section is while of key swap of lock comma key. That is the condition here. Until the key is set to false, we are going to be accessing the shared resource. We are going to be accessing we are going to be in the critical section, this entry section. We are going to stay in this loop. So now here let us consider a process P0, and trying to enter into the critical section initially. Now the value of the key is set to true, and then the while key, because it is true in the initial iteration, we are calling the function swap of lock comma key. Now here lock value is false, key value is true. Now when we are entering this swap function, we are swapping. Now lock will be becoming true, key will be becoming false. Here once this function swaps the variables and returns here, the value of the key will be false, meaning this loop is going to be terminated and the process P0 is given access to the critical section. Now P0 is having the access to critical section. Now P1, a process P1 is trying to access the critical section. Here for P1, key value is initially true, but key value is initially true because key is a value individual to each process, separate for each process and not a shared resource, and this lock is a shared resource. Now the value of the lock is true. Note that the value of the lock is true because P0 has set the value of the lock to true. Key equals to true for P1, and when it's trying to access this critical section, it is going to this condition while of key, while for P0 it is initially true, while of key for true, it is going to execute the loop for the first time. Swap of lock comma key. Here lock value is true and key value is true. So no matter how many times you are swapping these two, these two values, both are true. So until one of them becomes false, we are not having the access to the critical section in process P1. And when one of this is going to be false is when the lock, there is no way that key is going to be set to false by itself before lock. So the only way to exit this loop and have access to the critical solution is when the process P naught that is having access the process here. After all of this, we are setting the value of log to false inside the process, and when we are having access to critical solution is when the process P naught is completing its execution and setting the log to false. When process P naught is setting the value of log to false, then here key value after swapping log will be true and key will be false. Now the process P1 is having access to the critical solution, and after it is done with the critical solution, then again it is setting the value to false. So this is how the hardware solution swap and this hardware solution swap works. It is to be noted that the hardware solution is also used for when we are having only one instance of a resource. After this, we need to learn about semaphores. Semaphore is a shared integer variable. It is to be noted that semaphore is a shared variable that is an integer variable. Semaphore is a shared integer variable that holds the count of number of available instances of a resource. It holds the count of number of available instances of a resource. We can use semaphore whenever we are having only single instance or more than one instance, and this holds the count of number of instances available for a resource. So now there are two types of semaphores. One is counting semaphore, and the one is binary semaphore. The counting semaphore has a value of range between 0 to any number n, and the binary semaphore has a value of 0 or 1. The binary semaphore is used whenever we are only having one instance of a resource. For example, in most of the cases, we are going to be having only one instance of a printer, or one keyboard, or one mouse, or one monitor. So binary semaphore is used whenever we are having only one instance of a resource, and the counting semaphore is used when we are having more than one instance of a resource. For example, more than one CPU, a dual core, hexa-core, quad-core CPUs, or memory slots, or hard disks. So these are the two types of semaphores available. And coming to how we are going to use semaphores is, for semaphore we can't directly access a semaphore like how we are accessing the turn and flag variables in the other previous critical solutions. To access the semaphores, we need to call two atomic functions, two simple functions called wait and signal, or simply called P and Q functions. So how this is going to work is, whenever we are calling the wait function, we are internally checking if we have if we have at least one available instance. That is, the structure of the wait function is followed. We are going to pass the semaphore wait of S refers to the semaphore while S less than or equals to 0, an infinite loop, and after this S minus minus. This is structure. Here we are checking if S means semaphore holds the number of available instances. If the available instances are 0, then we are just waiting in the infinite loop, and once the available instances is more than 0, that is at least we have one available instance of the resource available, then we are getting the access to it and making the count to, we are decrementing the count by 1, letting them know that we have access, we are accessing one instance. So this is the structure of the wait function. And now coming to the signal function, here we are calling the signal function, we are calling the wait function before in the intersection, that is before accessing the critical section, before accessing the shared resource, and we are calling the signal function once you are completed using the shared resource, or when you are completed executing the critical section. So these are the two functions in the signal function. We are simply incrementing the count, signaling that we are done with using the shared resource. So these are the two functions in semaphore, and this is the usage. Now an example for places where we are gonna use semaphores is the different places where we are problems where we are gonna use semaphore is the common critical section problems, that are reader and writer problem, bounded buffer or producer consumer problem, and binding philosopher problem. So these are the three solutions where we are gonna be using the semaphores. So now coming to the reader-writer problem, in reader-writer problem, the problem definition is as follows. Whenever we are having a shared file, then and multiple processes are trying to access, we have four conditions. That is, all the processes that are accessing are readers, R star, that is any number of readers, and initially it is accessed by one reader or any number of readers and accessed by one writer, or it is initially accessed by a writer and it is now trying to be accessed by a reader, and a writer is already having the access and another writer is trying to access the shared file. So these are the four conditions, and inside these four conditions, we first, any number of readers can access. And in these three conditions, that is when any n number of readers are accessing and a new writer is trying to access, we cannot give access to him. That is first one. And when a writer is accessing and the reader is trying to access, then also we cannot give access to the reader. And one writer is already accessing and another writer is requesting for access, then also we should not give. Cannot access. So any number of readers can access at the same time. And then when readers are already present, no writer can access. When a writer is present, no reader or writer can access. These are the four conditions that we have. So now the algorithm for this is, we have both the reader structure and writer structure. Structure of writer. Here, weight of WRT. I am not going to write the structure for weight of signal functions because that's already known. Weight of WRT. Right? That is, once the weight of WRT, this is done. Once our process comes out of this weight function, we are directly writing it, and then signal of WRT. So this is the structure of writer, and coming to the structure of reader. mutex, and after calling weight of mutex, read count plus plus. Here we are having three variables, WRT, which is a Boolean semaphore, initially set to 1. We are having a mutex, which is mutual exclusion. The mutual exclusion that is accessed, mutex variable that is accessed inside the reader, initially set to 1. RD, which stands for the read count, which is initially set to 0. So these are the three variables. Now weight of mutex, read count plus plus with incrementing the read count, and if wait, here I selected the value variable name as rd plus plus. If rd equals 1, then weight of wrt, signal of mutex, read, and once we are done reading, we are then again calling weight of mutex, rd minus minus. If rd equals 0, if rd equals 0, then signal of wrt, and finally signal of mutex. So this is how this is the structure of the reader. And now an example, let us consider an example for this. Let us take an example for this. Consider an example where we are having multiple readers. Let's just take 2 readers. So now when the first reader is trying to access, that is R0 is trying to access, what's happening is weight of mutex, it's calling weight of mutex, and mutex value is initially 1, which is set to 0 by R0, and then RD plus plus, RD value will be set to 1. And after that, if RD equals to 1, RD here RD equals 1, so weight of WRT is called, inside weight of WRT less than or equals to 0, 1 less than or equals to 0, false. So we are not going to be staying in the loop, and WRT is set to 0. And after this, signal of mutex. Mutex is value is incremented by 1, so mutex will again be 1. After that, the first reader is performing some read operation. So now, while the R0 is performing some read operations on that, R1 also entered. When R1 entered, here initially we are calling weight of mutex. Mutex value is 1, 1 less than or equals to 0, false. So mutex will be 0, and after that, RD plus plus, read count will be set to 2. If RD equals to 1, RD is 2, so this condition will be false. Now signal of this, that means this block isn't going to be executed. Signal of mutex, so now mutex value is incremented and set to 1 again, and R1 is also reading. So the condition that we have is when multiple readers are accessing, any number of readers, that is any n number of readers can have access to the critical section at the same time, is happening, is possible. So now we have R0 and R1 inside the critical section. R1 has completed its reading and is leaving the critical section. So now what's happening is weight of mutex value will be set to 0, RD minus minus, reader count will be set to 1, and if RD equals 0, RD is not equal to 0, so this block is ignored, and signal of mutex will be set to 1 again. So now once this is completed, let us imagine we are having writer W0. writer W0 enter into the critical section. So now this is the structure of the writer. The writer program is following this structure, and initially the writer is calling weight of WRT, and here the WRT value is 0. 0 less than or equals to 0, true, meaning inside the wait function the writer is going to be staying in for while loop until this value, the WRT value, becomes 1. Here, until this reader reads, the WRT value won't be becoming 1. So the writer is not having access to the right part of the program, the critical section. That is the critical section. So the condition that when a writer when a reader is in the critical section, a writer must not access the critical section is true. So after this, the writer R0 is done with the reading and he is trying to leave the critical section. So what's going to happen is weight of mutex will, when the R0 is leaving, weight of mutex value will be set to 0, RD minus read count will be 0, reader count, and RD equals 0, true, signal of WRT. So now we are giving permission for any writer to write, and signal of mutex will be set to 1 again. So now, since WRT is set to 1, here the value of WRT is updated. So 1 less than or equals to 0, false. So the writer program, the R0 has left the execution queue. So now W0 is now given access to the critical section. So now W0 is writing. So when now W0 is writing, these are the instance values. So now let us imagine when W0 is present, a writer R0, the writer R0 has again entered to have access to the critical section to read. So now what's happening is, here the weight of when the writer is entering the critical section, WRT value will be set to 0 inside this function, and when reader R0 has come, it is initially setting the value of mutex to 0. Okay, mutex value is 1, 0. We are proceeding further. RD plus read count will be set to 1. If RD equals to 1, weight of WRT, RD equals to 1 equals 1, true, weight of WRT, inside WRT 0 less than or equals to 0, true. So now it's going to stay in the loop and not enter the critical section. So here when a writer is present, we are stopping any reader from accessing the critical section. This condition is also true. This kind of orientation is also checked. So that proves that when a writer is present in the critical section, we are not giving access to any other reader. So now when a writer W0 is present, another writer W1 has entered. So in this case, when W1 is entering into is starting execution, it's taking the weight of WRT. WRT value is 0, 0 less than or equals to 0, true, it's going to stay in the loop and it's not leaving the wait function, it's stuck in the loop, meaning that it's not having access to the critical section, and it's only having access when this W0 is done with execution. Consider that W0 is leaving the critical section, then signal of WRT value is set to 1, W0 has left the execution. Now 1 less than or equals to 0, true. Now write value WRT value will set to 0 and access is given to W. The critical section access is given to program W1. So this is the reader-writer problem. Here it is to be noted that inside the reader program, why we are having if RD equals to 1 and RD equals to 0 is because we are only updating, we are only taking the access of the write, we are disallowing write, we are doing the disallowing of write, we are doing that when the first reader is coming, and we are only giving access for a program to write when if only all readers have left the critical section. So this is the reader-writer problem, and after that we have a bounded buffer problem. Bounded buffer problem. The statement for the definition for the bounded buffer problem is when two processes, a producer process and a consumer process, are sharing a shared memory space, or in this case, let us just consider an array of size n. When they're sharing an array of n size, some any n size, then the producer can only write until the end, and whenever the shared memory space is full, then we are disallowing the producer from producing more until the consumer consumes, and we are disallowing the consumer from consuming when there is no data present in the shared memory space. So this is the condition that we have. The algorithm for this problem is producer. Here we have three variables: empty, which is set to n, full, which is set to 0, mutex, which is set to 1 initially. Here all the mutex is refers to mutual exclusion. Mutual exclusion means mutual exclusion means allowing only one process into the critical section at a time. Allowing only one process to enter into the critical section at a time is called as mutual exclusion. Here this variable mutex is a binary semaphore that is used to provide us with mutual exclusion. Now, these are the three variables that we have. Inside the producer, the structure of the producer is follow: weight of empty, weight of mutex, produce, signal of full, signal of mutex. Here it is to be noted that these three are shared variables. So now this is the structure of the producer, and the consumer structure is weight of full, weight of mutex, consume, signal of empty, signal of mutex. So this is the structure of the consumer. So the way it is done, the way this algorithm works is, here the empty variable stores the number of empty spaces in the shared memory or the buffer. The number of empty spaces in the buffer is held by empty variable. The full variable stores the number of occupied, the number of buffers, the number of containers in the buffer that have data present in them. Mutex is a binary semaphore that only allows one producer or consumer to work at once. So now how it's going to work is, let us consider a buffer of size 2, just 2. So now empty, and here n equals to 2, that is the size of buffer, empty equals to 2. So now initially a producer is trying to produce some data. So now what's going to happen is, here empty value is 2, full value is 0, and mutex value is 1 initially. When producer is accessing weight of empty, here we are checking 2 less than or equals to 0. 2 less than or equals to 0. True less than or equals to 0 is false. So now empty minus empty value will be becoming 1, and weight of mutex 1 less than or equals to 0, false. So mutex value will be set to 0. and the producer is producing some data, let us say 10, and after it's done producing, it's calling the signal on full, meaning full plus plus, so full value will be becoming 1 from 0, signal of mutex, now mutex is also becoming 1. So here at this instance it is to be noted that these value tell how many containers do we still have empty to write some data. The full tells how many containers we have data present. We can consider it as that. So here we have one empty space, one space where we have data present. Mutex equals to 1. No process is active. No consumer or producer is active. So now again a producer is trying to produce some data again. So weight of empty value is set to 0. 1 less than or equals to 0, false. So empty value is set to 0. Weight of mutex will be 0. Producer producing 13. After that signal of full. So full value will be set to 2. Signal of mutex will be set to 1. So here we have 0 empty spaces in the buffer, 2 containers that have data, no process that is actually in the critical section. And now when a producer is trying to produce one more data, let's see how we are disallowing it from entering one more data. Here weight of empty is 0 less than or equals to 0, true. So it's going to be stuck in the loop inside the wait call. And the producer is unable to proceed further until we have an empty container. So now let's just leave this producer aside. So now coming to the consumer, let us say we have a consumer trying to consume some to read some data. So what's happening is weight of full value is 0, full value is 2 less than or equals to 0, false. So full will be becoming 1. Weight of mutex will be becoming 0, 1 less than or equals to 0, false, so it's becoming 0. The consumer has consumed 10, let us say 10, and then signal of empty. Since it consumed 10, here empty value will be set to 1. Signal of mutex value will be set to 1. So now because here we have one empty container, this producer is able to leave this call because the value of empty is updated. 1 less than or equals to 1 less than or equals to 0, false. So it's leaving this. Weight of mutex value will be set to 0. Producer produced some more data, 20. Signal of full, 2. Signal of mutex, 1. So now the consumer is trying to consume some more data again. Weight of full mean 2 less than or equals to 0, false. So full value will be becoming 1. It consumed 13. Weight of mutex 0. It consumed 13. And after consuming 13, signal of empty 0 will be between 1. Signal of mutex 0 will be between 1. Now consumer is trying to consume again before any other producer is producing some data. So here weight of full again 1 less than or equals to 0, false, will be between 0. Mutex again becoming 0. Consumes 20. Signal of empty will be 2. Mutex value will be 1 again. So here we have no data present, no producer is ready to produce, and no data for the consumer to consume. So we have to disallow consumer from consumer. Now when a consumer is coming again, when a new consumer is trying to come and consume some data, weight of full value is 0 less than or equals to 0. That means it's going to be stuck in the loop, meaning that we are disallowing the consumer from consuming data until a producer is producing some more additional data. So this satisfies our conditions of producer cannot produce any more data once the buffer is full. Consumer cannot consume any data once the buffer is empty. This algorithm complete follows those two conditions. So this is the bounded buffer problem. And after that we have dining philosopher problem. The statement for this, the definition for this problem is: given a circular table around which an n number of philosophers are sitting, and we have n number of chopsticks available, with food served in front of each philosopher. Now, the problem here is we have n philosophers with n chopsticks, and they have food served in front of him. Now, the philosophers must eat. But each philosopher needs two chopsticks to eat. Each philosopher needs two chopsticks at a time to eat, and all philosophers must be present at the table at a single time. So this is our problem. Now, considering that we only have n chopsticks at a time, each philosopher is only getting access to one chopstick. Considering that every philosopher is picking up one chopsticks at all time, is holding one chopstick at all times. So now we have to disallow philosopher. Say this is P0 1 2 3 4 5 6 7, C0 1 2 3 4 5 6 7. We have to disallow when P0 when P0 wants to eat. We have to disallow P7 from holding its chopstick. When P0 is ready to eat and picks up C0, we have to make sure that P1 is not picking up the chopstick P1. What we are doing, we need to check. We need to disallow P1 from picking up the chopstick P1 C1, so P0 can have both C0 and C1 to eat. That is our problem. So in simple, we are disallowing the processes that are beside us, to the right of us and to the left of us, from picking up the chopsticks. That is our problem. So now if all the processes are picking up the chopsticks, then we are stuck in a state of circular waiting, where each process is waiting for other process and no process is able to move further, which will lead to a deadlock. So now the solution for this can be weight of chopstick of I, and then again weight of chopstick of I plus 1 mod n E signal of chopstick of I, signal of chopstick of I plus 1 mod n. So this is our algorithm using semaphores. This is one way that we can take, but there are some drawbacks with this case. That is, now imagine 5 philosophers. 1 1, 2, 3, 4, 5. This is the chopstick array. 0, 1, 2, 3, 4. Each chopstick is free initially. 1, 2, 3, 4. 0, 1, 2, 3, 4. So now, following this algorithm, coming to P naught, when P naught is executing, chopstick of 8 or chopstick of I, here, chopstick, this is the chopstick array, chopstick of I is 1, so is free, meaning we are picking it up, chopstick of I plus 1, 0 plus 1, so that is this chopstick, that is to the left of P naught, is free, so we are picking it up. So now, P naught is started eating. Now coming to P1, when P1 is trying to access its chopstick, that is chopstick of 1, weight of chopstick of 1, here this is 0, 0 less than or equals to 1, 0 is true, meaning P naught is unable to eat, is unable to pick up the chopstick. So it's going to be staying in the loop, it's going to be stuck in the loop, meaning P naught is unable to proceed with eating. Now P2, chopstick, weight of chopstick of 2 is here, chopstick of 2 is 1, so we will give it access. Value will be set to 0, and here to the left of Z2 plus 1 equals mod 5, 3 mod 5 equals 5, chopstick of 5, chopstick of 3, so 3 mod 5 equals 3, chopstick of 3 equals to 1, set to 0, meaning P2 is proceeding with eating. Now same with the P3, chopstick of 3, weight of chopstick of 3 is 0, 0 less than or equals to 0, true, it's stuck in the loop, so P3 is unable to eat. Now coming to P4, for P4, chopstick of I, that is chopstick of 4 is 1, so is set to 0, and now chopstick of I plus 1 mod 5 or mod n, that is 4 plus 1 mod 5 equals 5 mod 5, 0, that is this is 0, so it's going to be stuck at here. So P1 and P3 are stuck at this stage, P4 is stuck at this stage where it is picking up the chopstick, its chopstick and waiting for P0 to give it the other chopstick. So P0 is having 0 and 1, P2 is having 2 and 3, P4 is having 4. Let us see. Now these are the chopstick head, and P1 is waiting for 1 and 2, P3 is waiting for 3 and 4, P4 is waiting for 0. So now can imagine P2 is completed eating, meaning signal of chopstick of 5, signal of chopstick of 2, this value will be set to 1, I plus 1 mod 3, that is this chopstick, is set to 1. So these two are free, meaning P3 has access to, is now can access chopstick 3, and P3 is picking up this. So this is done with eating. P3 picked up chopstick 3. So now P3 is waiting for chopstick 4, but chopstick 4 is being held by P4. Even though P4 is not eating and is also waiting for P0, here P3 is also unable to further proceed because P4 is holding chopstick 4, but it's not eating. So this is the problem that we are having with this solution of semaphores with when coming to the dining philosopher problem. That is why we are having another solution for dining philosopher problem with monitors. A monitors is a high level abstraction of which is effective. That is, inside a monitor In a monitor, all the resources a monitor is a high level abstraction in which we are having all the initialization code inside it and all the resources and also procedures inside it, meaning that all the processes and resources are available inside the monitor itself along with the initialization code, due to which all the handling of the critical sections, handling of the shared resources is done by itself, meaning there is less wastage of resources and no need of no need of any intervention from the user or a lot of intervention from the kernel to handle the shared resources.